So today we're going to discuss definite integral. So to start with the definition of integral. So let f of x be a continuous function defined on an interval a, b. Then the area of the graph of f of x and the x-axis is called the definite integral of f of x between a and b. For example, in the figure opposite, so the shaded area A shows that the definite integral of f of x on the interval AB. So we can write this expression as A stands for the area is equal to the integral of f of x dx from A to B. So this is now the illustration of the graph. So this is now the area from A to B. Okay, so the definite integral, we have the lower limit, which is now a, and the upper limit, we have b. So we know that f of x is the integrand and dx is the differential. Note that if the graph is below the x-axis, then its integral will be negative. However, the area is a positive quantity, so we reverse the sign. So we can write now area, or A, is equal to the negative of the integral of f of x dx between A to B, or from the interval of A to B. We say that the definite integral can be negative, but the area is always positive. So this is now the graph of our definition here, that if the area is below the x-axis, then the area itself is a positive, but we can just indicate negative when it is below the x-axis. Now, the other one is that if part of the graph is below the x-axis and the part of the graph is above the x-axis, then the graph will be the algebraic sum of the areas. So in the figure, all of the areas A, B, C are positive numbers. So the integral of f of x dx between A to B is equal to the area of A minus the area of B plus the area of C. As you can see in the graph, the area of A and C is above the x-axis and the area of B is below the x-axis. That's why we indicate their negative sign. Now let's put this one into example. We have find the area of the region bounded by the graph of y equals 3x and the x-axis on the interval of from 0 to 4. So we have here the graph. So we know that this is now the area from A to B, that is now from 0 to 4. Okay, and we have the equation is y is equal to 3x. Okay, so to solve for that, we are going now to write first the formula. So we have the area is equal to the integral of f of x dx between a to b. All right, so we could say that the area is equal to the integral of f of x dx between a and b, where a and b are the interval. So writing now the given, so we have a is equal to the integral of, the meaning of f of x is just equal to y equals 3x. So therefore we have now 3x dx evaluated from 0 to 4, or between 0 to 4. So I integrate it first. We have the integration of 3x dx is equal to 3x squared over 2, and this will be evaluated from 0 to 4. So we can write now the given of the interval. So start first with the upper interval minus the lower interval, or the upper limit minus the lower limit. So we have 3 times the value of the upper limit is 4. Then we have squared all over 2 minus 3 times, substitute the value of the lower limit, which is 0, squared over 2. By simplifying, we know that the second term is just equal to 0. Then we will just simplify on the first term. We have now, we have 4 squared equals 16 times 3 is 48 and then divided by 2. So this is now equal to 24. Okay, this is now 24 square units. Okay, number 2, in the figure, the areas of the shaded parts of A, B, and C are given as A equals 7 centimeters squared, B equals 9 centimeters squared, and C equals 8 centimeters squared. Find the total area of the shaded region in the figure and evaluate the integral on the interval a, B. So let us write first the formula. So we have, since this is now, we are talking about the total area of the three regions of A, B, and C. So we can write first the formula of total region. So we can write now as the area A plus B plus C. Now, we know that all of these areas are given. So by substitution, we have now area A is 7 centimeters squared plus 9 centimeters squared plus 8 centimeter squared. Okay, so adding that one, it has a total of 24 centimeter squared. So that is now our total area. But we also asked to find the total of the shaded region in the figure that is now 24 centimeters squared, and we are going to evaluate the integral on the interval between A to B. So we're talking about these limits or the intervals. So we can write now, we have the integral on the interval A B. So the formula for this now will be equal to the integral of f of x dx evaluated from A to B. So we can write here according to the graph. So we have the area is positive area, then B now is negative. So we write because it is below the x-axis. So therefore we have minus B plus the area of C which is above the x-axis. So we just write positive C. So by substitution now, we have A is 7 centimeters squared minus B is 9 centimeters squared and the area C is 8 centimeters squared. Then by simplifying, it will give us now 6 centimeter squared. So I hope you can see the difference between these two questions. So the first one is asking for the total region. So add everything. But if we are asked to evaluate the integral on the interval AB, then you have to consider the position of the areas. When it is above the x-axis, then it be all positive. Then it be when it's below the x-axis, then if you write, you indicate there the negative sign, as like what we did here for the area B. So next we have here the fundamental theorem of calculus. So let f of x be a function such that the function is with the interval of AB will yield to a real number. If the f prime of x is equal to the f of x and the integral of f of x dx is equal to f of x plus c, then we have the formula of the integral of f of x dx between a to b is equal to the antiderivative plus a constant, then evaluated from a to b. Then that would be simplified. We are going to substitute the value of x, start now from the upper limit minus the lower limit. So this is what I use in the two previous example. So we have here now the f of b minus f of a, where b there is the upper limit and a there is the lower limit. So here we use the notation of this symbol of a to b to show that the boundaries of the integral. So we have we have to note that the fundamental theorem of calculus shows us that we do not need a constant of integration of c when we evaluate a definite integral. For example, suppose we rewrite f of a plus c instead of f of a and f of b plus c instead of f of b. Okay, no need to write the concept of integration when we are dealing with the definite integral. Then, by the fundamental theorem of calculus, the integral of f of x dx between a to b is equal to f of b plus c minus f of a plus c. If we're going to simplify that one, the constant c there will be cancelled. That is why we have the formula of f of b minus f of a. So this is what I'm trying to say a while ago, that if we are going to simplify that one, so this one, the positive c there and the other negative c will be cancelled. That is now the remaining terms. We have f of b minus f of a. And this term is what we call now our formula using the fundamental theorem of calculus. This is now the antiderivative after we evaluate the given integrand. Okay, so that's the formula now, and we call that one as the fundamental theorem of calculus. Now let's discuss first regarding the properties of definite integrals. The definition of the definite integral of f on the interval ab specifies that a is less than b. Okay, that's why we call a is the lower limit and b is the upper limit. Then it should be a is less than b. Now, however, it is convenient to extend the definition to cover cases in which a is equal to b or a is greater than b. Geometrically, the following two definitions seem reasonable. For instance, it makes sense to define the area of the region of with zero width and finite height to be zero. Now, these are the definitions of two special definite integrals. Number one, if f is defined at x equals a, then we define f of x dx evaluated from a to a. So since the limits or the intervals are the same, then our answer for that will be 0. Now, number two, if f is integrable on the interval ab, then we define the integral of f of x dx from b to a. So we know that in our assumption that a is less than b, then if that's the case, class, then we are going to put negative sign before the integral sign of f of x dx from a to b. So in other words, these two expressions are just equal if we are going to put a negative sign. Okay, so it's in order for you to start now from the lower limit to the upper limit, because we assume a while ago that a is less than b. So if that's the case, class, then you have to change the position of the limits. Then we have to put the negative sign. Okay, now let's try to put all these in exercises, the one that we studied about the properties and the fundamental theorem of calculus. So we are going to evaluate the definite integral. Okay, so we have now the integral of 2x dx evaluated from negative 2 to 1. Okay, so let us take the integration for that. So the integral of 2x dx is equal to 2x squared over 2. So 2 will be cancelled. So we have x squared. Then this will be evaluated from negative 2 to 1. So in that case, class, the lower limit is -2 and the upper limit is 1. So we don't need to write negative sign as what we have discussed on the last slide. So we have now to use the fundamental theorem of calculus. We have now x is will be replaced by 1 and this is now squared. We have now 1 squared minus -2 squared. So 1 squared is just equal to 1 minus the square of -2 is 4. So 1 minus 4 is equal to -3. Now for number 4, we have the integral of sine x dx. So we know that the integral of sine x dx is equal to negative cosine x, then this will be evaluated from pi to pi. According to the properties a while ago, we have this one, number 1. So if the function f is defined at x equals a, then we define if the limits are just the same. So using this definition of the definite integral, so definitely our answer will be equal to 0. So using that one, or then we can just conclude that the integration for that will be 0. But for the sake of computation, so we will just use the substitute. We just use a substitution. So we can write now. We have negative cosine. Okay, we'll replace x by pi. So we have the negative cosine pi. Okay, minus the negative of cosine pi. So by simplification, so we can write now the value of, so this will be now the negative cosine pi, negative and negative times negative cosine pi, we have now positive cosine pi. So even without using the exact value of pi, but because this expression give us an additive inverse, therefore this is now equal to 0. Or as I have said earlier, you don't need now to use substitution. You just state these definitions of two special definite integrals like number 1. So you can just use this definition to justify your answer. All right, let's move on to example number 5. So we have the integral of the quantity of x plus 2 dx evaluated from 3 to 0. Take note, our lower limit is bigger compared to the upper limit. So in that case, class, we are going to use this property number 2 or definition number 2. If f is integrable on interval ab, then we define the integral of f of x dx from the upper limit, which is written below, and the lower limit written at above. So we have to write the negative sign in order for us to interchange the writings of the limits. Okay, so let's apply that one, property number 2. So because of this one is bigger and the other one is smaller. So I will write first negative sign, and then I'm going to interchange the limits. So started now below, which is now 0, which is smaller compared to the upper limit is, which is bigger, which is 3. Then right now x plus 2 of dx. So let us try to integrate. So the first term now will give you x squared over 2 plus the integral of 2 dx is equal to 2x. So this will be evaluated from 0 to 3. I forgot to write the negative sign. So we have now to simplify. We have the negative of, we write now x by, substitute x by 3. So we have 3 squared over 2 plus 2 times 3 minus, we have replace x now by 0. So we have 0 squared over 2 plus 2 times 0. All right, so we have now, so on the second term, this one. 0 squared is 0 over 2 is 0 plus 2 times 0 is 0. That's why we just cancel that one. And we have 3 squared is 9 over, we have now 9 over 2. So 3 squared is 9 over 2 plus 2 times 3 is equal to 6. And just adding the fractions, so it will give us now, take note we have negative sign outside, that's why our answer must be negative 21 over 2. Alright, so let's move on to the other property. We call this one as additive interval property. So if f is integrable on the three closed intervals determined by a, b, and c, then the integral of f of x dx between a to b is equal to the integral of f of x dx evaluated from a to c plus the integral of f of x dx evaluated from c to b. So take note of this class. So if we are dealing with the three closed intervals, so one of the interval there must be written in this form. So this is now the upper limit, and the other one should be written in the lower limit. So algebraically, this will be cancelled. That's why it will go back to A to B. Okay, so we have now example number 6. We have the integral of the absolute value of x dx evaluated from negative 1 to 1. We know that in the idea of absolute value of x, then there are two possible values of x, which is now the negative x and the positive x. Okay, that is for absolute value. So in writing that in our equation, so this will become now, we have the integral of, we have negative 1 to 0 of negative x dx plus the integral of positive x dx from 0 to 1. So in other words, class, our a is negative 1. So following this one, that's a. This is our a. And our b is this one. So we have negative 1 to 1. So this is now the same as if, from the interval between negative 1 to 1 or a to b. So it happens that our c there in our example, it's the absolute value of x, so this will give you 0. Take note in the, let's recall on this, we have the absolute value of x. There are two possible answers. The other one is negative x and the other one is positive x. Okay, so negative x when it is now less than 0, and we use positive x when it is now greater than or equal to 1. Okay, so we have now to solve for this. So let us integrate. We have now the integral of negative x dx can be written as negative x squared over 2. And we are talking here about the first integrand. So this will be evaluated from negative 1 to 0 plus for the second integrand or the second term, so the integral of x dx is positive x squared over 2, and this will be evaluated from 0 to 1. So by substitution, so we have now the negative of 0 squared over 2 minus, we have we have the negative of negative 1 squared over 2. Okay, then the second term will be plus, we have now 1 squared over 2 minus 0 squared over 2. So this is now the second term or the second, and this is now our first term, the evaluation, using the fundamental theorem of calculus. Now, so by simplifying this one, so this is now the square of 0 is still 0 times negative still 0, therefore 0 over 2 is 0. Okay, that's now 0. This one now is, we have the square of negative 1 is 1. So over 2, that's 1 half. Positive 1 half times negative becomes a negative 1 half. But we still have another negative here. That's why it becomes positive 1 half. So I can write here positive or just 1 half. Now this one, so we have simplify. 1 squared is 1. So 1 over 2 is 1 half. And 0 squared over 2 is 0. So we have now another 1 half for the second term. 1 half plus 1 half, so is equal to 1. So that is now the value of when we integrate the absolute value of x dx from negative 1 to 1. So next property, we have the properties of definite integral. So we call this one theorem 4.7 in this book that I've used. So if f and g are integrable on closed interval ab and k is a constant, then the functions kf and the sum of the two functions f and g are integrable on the closed interval ab. Now we have number one, the integral of kfx dx between a to b is equal to k times the integral of f of x dx uh, between a to b. So k there is just a matter of constant multiplier that we have learned in a previous topic. So number two, we have the integral of the sum of the two functions of dx evaluated from a to b, so is equal to the integral of f of x dx from a to b plus or minus the integral of g of x dx from a to b, or evaluated from a to b. Note that property number 2 of this theorem can be extended to cover any finite number of functions. So meaning to say we can add as many as we can the functions. Okay, so here's the other example below. So we have now another example, number 7. We have the integral of um, the quantity of negative x squared plus 4x minus 3 of dx evaluated from 1 to 3. So let us integrate it first. So the first term will give us negative x cubed over 3 plus 4x squared over 2 gives us 2x squared. The integral of negative 3 dx is negative 3x, and this will be evaluated from 1 to 3. So by substitution, start now using the fundamental theorem of calculus, which is the f of b minus f of a. So we have the negative of 3 cubed over 3 plus 2 times 3 squared minus 3 times 3. So this is now our f of b minus the f of a. We're going to replace x by 1. So we have the negative of 1 to the third power over 3 plus 2 times 1 squared minus 3 times 1, then close. So simplifying, so this is now, we have 3 cubed is 27, then divided by 3, that is now 9, and we have negative out sign, so this is now negative 9. And we have plus 3 squared is 9 times 2 is 18. So this is now positive 18. And negative 3 times 3 is negative 9. Okay, that is now the value of f of b minus f of a. We have 1 cube is 1 over 3 times negative. So we have negative 1/3. And this one is 1 squared is 1 times 2. So that is now positive 2. And the last term is 3 times 1 is negative 3. So simplifying this, we know that the first term now, or the value of f of b, is equal to 0 because negative 9 and negative 9 is negative 18 plus 18. So this will be now equal to 0. Now, the next term we have, or the value of f of a, we have let's try to combine first. 2 minus 1 is negative 1, so we'll just have negative 1 third minus 1, because of 2 minus 3, that's now negative 1. So that is now equal to negative 4 over 3. But there is negative before this quantity, so therefore it will give us now 4 over 3. Okay, so this is our answer for number 7. So next we have number 8. So they are almost similar, class. So we have now integrate this one. We have 2x squared dx is 2x cubed over 3. So we have 2x cubed over 3 plus 3x squared over 2 minus 4x. So evaluated, this will be evaluated from 1 to 3. So they are just the same in limits, but the integrand are different. So let us substitute. So we have 2 times 3 cubed over 3 plus 3 times 3 squared over 2 minus 4 times 3. So this is our f of b minus the f of a. We have replace x by 1. So 2 times 1 cube over 3 plus 3 times 1 squared over 2 minus 4 times 1 close. All right, so simplify. So we have, let us solve for that. So the first term now, 3 cube is 27 divided by 3, or using the law of exponent, we have 3 cube over 3. That is, now we have to subtract exponent. So therefore, we have 3 squared is 9 times 2. We have now 18 plus 3 squared is 9 times 3. We have 27 over 2. That's why 27 over 2 minus 12. So on the value of f of a, we have 1 cube is 1 times 2. We have now 2 thirds. So we have to use open parentheses. So the second term we have plus 3 over 2 minus 4. So we're going to simplify that one. So we have 18 plus 27 over 2 minus 12, or you may combine first 18 minus 12, that is now 6, and then plus 27 over 2. So we have now the answer of 39 over 2 minus, we have 2 thirds plus 3 halves minus 4. So it will give us negative 11 over 6 times negative outside. So this becomes now 11 over 6. And then combining the two terms, we have 39 over 2 plus 11 over 6. So it will give us now the answer of 64 over 3. All right. So let's move on to the next. We have number 9. We have the integral of x squared minus 5x plus 1 over x of dx with the interval from 1 to e. Now let us divide it first. So we have to divide our integrand. So this will give us x squared over x is x minus 5 plus 1 over x of dx. So the interval from 1 to e. Now let's take the integration of the first term. We have x squared over 2 minus 5x plus the integral of 1 over x dx will give us ln of the ln of x, or the ln of absolute value of x, or just write ln of x, and this this will be evaluated from, I will just write here the absolute value of x, and this will be evaluated from 1 to e. So by substitution, start now with the upper limit, or the f of b minus f of a, by virtue of the fundamental theorem of calculus. So we have e squared over 2 minus 5 times e plus ln of the absolute value of e. So this is now your f of b minus f of a. Now we have replaced x by 1. We have 1 squared over 2 minus 5 times 1 plus ln of 1. The absolute value of 1. So by simplifying, this is now, we have e squared over 2 minus 5e plus ln of the absolute value of e is 1. Okay, minus 1 squared is 1 over 2 is 1 half minus 5 plus ln of 1 is 0. So since ln of 1 is 0, so I'll just write there 0 to know that it is 0. Now we have to, I'm going to combine like terms, including the f of b minus f of a. We have now e squared over 2 minus 5e plus 1. Negative times 1 half is negative 1 half. Negative times negative 5 is positive 5. So combining like terms, so we can write now e squared over 2 minus 5e. So these one are all constants. So we're gonna combine that one. So 1 plus 5 is 6. And 6 minus 1 half. So that is now 11 over 2. We have plus 11 over 2. And if we're going to uh, combine it all, having a common denominator of 2, so we can write now a common denominator of 2, or you can just stop your answer up to this point if you want. But so for the sake, we are going to simplify. So we have now, so we will just simplify further. So we have e squared minus, this will be 2 times 5 is 10e plus, we have now 2 divided by 2 is 1 times 11 is 11. So we have the final answer now of e squared minus 10e plus 11 over 2, or either of these two answers I will accept up to that point. All right, so I have another example. We have the integral of sine x plus cosine x dx between 0 to pi over 2. So we have to integrate. So the integral of sine x dx is negative cosine x plus the integral of cosine x is positive sine x, or just sine x, and this will be evaluated from 0 to pi over 2. All right, so by substitution, I can write now here as negative cosine of pi over 2 plus sine of pi over 2, and then minus, this is the f of b minus f of a, which is now the lower limit. So we have the negative cosine of 0 plus sine of 0. So to solve for that, we have now negative cosine of pi over 2 is 0. Okay, by the way, class, before we're gonna substitute, make sure your calculator is in the radian mode. All right, so cosine pi over 2 times negative, so it's still 0, and sine pi over 2 is also 0. and then minus, we have negative cosine of 0 is negative 1, and sine of 0 is 0. So therefore, this is now 0 here. We have negative 1 times negative outside, so therefore the final answer is 1. And for next number, we have the integral of the square root of 3x plus 1 dx if between 0 to 1. Okay, so last time with our discussion, I already introduced to you uh, a little bit background of substitution method, because we are not yet there yet in the proper lesson of integration by substitution method. So I have I was able to share a little bit of knowledge of substitution. So we will try to use that one here. If u is equal to 3x plus 1, then derivative of u is du, and derivative of 3x plus 1 is 3 dx. So dx can be found here as part of the given, and we also, but we have du is equal to 3 dx, then we have to define dx by dividing both sides by 3. So therefore dx is equal to du over 3, or you write there 1/3 of du. Now we can rewrite the given. So we have now 3x plus 1, square root of 3x plus 1 can be written as we have 3x plus 1 to the power of 1/2 of dx from evaluated with the interval between 0 to 1. Or we can use now substitution method. So we can write now the meaning of 3x plus 1 is u. So we have u raised to 1/2. And the meaning of dx, as we define here, we have times du over 3. Then we are going to write the constant multiplier. So this can be written outside. So we have 1/3 the integral of u raised to 1/2 times du. Now we are going to use the power rule. So we have u raised to 1/2 plus 1. So 1/2 plus 1 is equal to 3 over 2. So I will just write first here 1/2 plus 1. So this will be evaluated from 0 to 1. So simplifying this one now, we have u to the power of 3/2. Then over 3/2, take the reciprocal. So this becomes now 2/3 of u raised to 1/2. And this will be evaluated from 0 to 1. So we are going to change first or substitute the meaning of u. So we have 2 times the quantity of 3x plus 1, and this will be raised to the power of 3/2 all over 3, and this will be from the interval from 0 to 1. So we have to to substitute. We have now 2/3 times 3 times the value of x is 1 plus 1 to the power of 3/2 minus 2/3 times 3 times the value of x is 0, then plus 1, then raised to the power of 3/2. All right, so we have, all right, so start here, start inside the parentheses. So 3 times 1 is 3 plus 1 is 4. Then what is the square root of 4? We have 2. Then 2 raised to third power is 8. And then 8 times 2 thirds, we have 16 over. Okay. Going back again, class. So I forgot to write 1/3 here. All right. So 1/3 times 2/3. This becomes now. I will just write here 1/3. So we have 1/3 times 2/3. So this becomes now 2 over 9. So this becomes now 2 over 9, as well as this, so 2 over 9. Okay, so this will be also 2 over 9. All right, so again, let us simplify. So 3 times 1 is 3, plus 1 equals 4. Take first the square root of 4, which is now 2. Then 2 raised to the third power is 8 times 2 over 9. So this will give us 16 over 9. Minus 3 times 0 is 0, plus 1 is 1. And the square root of 1 is 1. To the third power, then 1 to the third power is 1 times 2 over 9. So we have now 2 over 9. So this similar fraction. So we will just subtract the numerator. So 16 minus 2 is 14. Then copy the common denominator of 9. So that is why our answer now is 14 over 9.